Welcome back, and in this video we're going to take a quick view or quick look at the logistic regression model, which serves as our baseline or basic model that we will use if the target variable is a binary variable. Okay, so previously we discussed about the linear regression model and what is applied to what we call in general a regression task, but assume now we have a classification task, and in our case here we have a special classification task which is binary, so it's black or white, male or female, bi or not bi. So everything that you can encode with a 0 and a 1 typically. So 1 usually represents the label we directly model. So I don't know, for instance, if a person is buying an object or something like this, and the referent or the other category is encoded with a 0 typically. Okay, so usually we have a target variable which is encoded in 0 and 1, and each number representing one disjoint category, and overall we have two categories for each observation that can occur. So a person either buys something or it doesn't buy anything, or it's a male or it's a female, and so on and so on. Okay, so in the linear regression model, we get an output from a model which is a simple real valued number. Okay, so the problem here is obviously if we use this, then we may get numbers which are different from 0 and 1. So the model is not really suited to provide predictions for a binary classification problem. Now, strictly speaking, what we need now is a model that either returns a 0 or a 1. This can be done with the logistic regression model, but, and this is a rather big but, which is often forgotten, what the logistic regression model does is not really making predictions which are encoded in 0 and 1s. It predicts probabilities. Okay, so it gives us a probability estimate given the information of the feature variables. How likely is it that the person is going to buy this object? Okay, so the output of a regression model typically represents a probability for being the category of interest, which is directly modeled, which can can be defined by you as the user. And so, but still, in comparison to the linear regression model, which gives us real valued numbers on the whole range of possible values, even though we model a probability as we need a number which is obviously between 0 and 1, because probabilities need to be between 0 and 1. And basically, this is like the first of two things that we need to change with respect to the linear regression model, but the rest remains quite similar. Okay, so we are given here in a general setting where we have a prediction model. So that was how we had it for the regression model. So here n is the number of feature variables, and the regression model is simply, in our case, the dot product between the feature variables and our parameter estimates of the model. And now if we enter the n feature variables, we get a single number as an output, which is a real valued number. Now for the logistic regression model, we need to even though we first in the first step get a real valued number, we still need now to map it to the range between 0 and 1, because it represents a probability. And this is achieved by generating, or by using, what is mathematically called a composition. So basically we're going to do the same as for the linear regression model, but then compose this function with another function which makes sure that those real valued numbers are mapped to the range which can be used for probability estimates. So are mapped to the range of 0 and 1. So the overall composition use n feature variables as the input and outputs a number which is between 0 and 1 and represents a probability estimate for the probability of the observation belonging to the target category of interest. How do we succeed here? by taking an appropriate function which is composed of with the linear prediction function of the linear regression model. And one of the most popular choices can be seen here. So assume now the Z value here is the output that you usually would get from the linear regression model. And if you insert this output into the so-called sigmoid function, or it's also called the standard logistic function, which is defined as you can see here, then you see the value range of this function is between 0 and 1, so it kind of suits quite well for our needs. Obviously, this is not the sole and single function that can be used here. There are many functions which are have the value range between 0 and 1, but this is like the most popular choices nowadays. For instance, another example which is also quite common would be the probit function, yeah, which stems from the cumulative distribution function of the standard normal distribution. Okay, so and basically that's it when it comes to the question how we generate predictions for our binary target variables, because we do the same thing. So the parameter estimates that are necessary are the same as for the linear regression model, but we do not stop at the output of the linear regression model. We further insert the value that would come from a linear regression model into another function, which maps this value to the range between 0 and 1, and is then interpreted as a probability for being a specific category of the target variable. Okay, and so we will denote this by now calculating the prediction with P, so it stands for probability, and it represents the probability of the target variable being category 1. As I stated before, it depends on you as a user, so you could define which of the two possible outcomes of the target variable is category 1. So for instance, if we say we're interested in if the person is buying something, then it makes sense that we use 1 if really a person bought something in the training data set, and 0 otherwise. And otherwise always, in this example, would mean it didn't buy anything. Okay. So implicitly, as we have two disjoint possibilities that can be realized with respect to the target realization, the probability of buying something also implicitly defines the probability of not buying anything, because these are disjoint possible outcomes. And so the probability for the other category is 1 minus the probability for the interest for the target of like the category which interests us the most. As you can see here, parameters, as I also stated before, so just like this expression here is what we used for the linear regression model, and now this expression still depends, like the overall expression which is used for the logistic model, still depends here in our case on a set of parameters that are used by first calculating the dot product. So we have the number of feature variables plus the one that we need for the intercept as parameters. So the number of parameters which need to be estimated is the same as for the linear regression model. So yeah, given we have some parameter estimates here, so for instance, if we would have one feature variable, then we would have our constant, so the parameter set to 1, and this is the parameter that belongs to the feature variable. Now this would be the output that we used for the linear regression model, so in this example would be a value of 5. And if we now insert this into the sigmoid function, you can see what happens here. So high positive values map the original input to a value which is close to 1, so to a probability which is close to 1, and the more negative the value is, the lower would be the probability for being the specific category 1. And so as we have probabilities, the question still remains. Our original task is really we need a decision. So we need a decision. Will this person buy stuff or will it not buy anything? So, and even though the probability is high, it doesn't mean that the person will buy anything for certainty. So obviously we need to define some boundary, at which we say, okay, the probability is so high that we really believe the person will buy something, or it won't. And like the intuitive boundary which you can use in the first step, maybe here like 50%. So if the probability prediction is higher than 50%, then we decide that the estimate or the prediction for the actual target variable is equal to 1 and 0 otherwise. Obviously, this is something which can be set by you as a user, and so should also be subject to some sensitivity analysis, and you should also, examine if how this changes the capability of your model for really predicting the correct target specifications here if you change this boundary here. Okay, but we'll take a look at this at a later step. The shape of the probability function is driven by the parameter estimates. So if we stick to a simple example which uses a single feature variable, this is just some examples that show you how the parameters that are again going to be calibrated by the estimation process have a real impact on the probability predictions, and by this means on the predictions of the outcome that we are predicting for the real target variable. Okay, so for instance, take a look here. If we have the intercept here, then it would shift the curve to the left or to the right. The higher the value which is on the feature variable here, so theta 1, the more steep it gets. And if it has a negative sign, as you can see here for the orange line, then the type of relationship is inverted. Okay, so yeah, just play around with this by yourself, or maybe try to define it by yourself, or just take a look and give it a good thought here. This just should illustrate you again that really choosing the parameters is like the sensitive task that we need to do appropriately in order to determine appropriate probability predictions, which in the end should help us to really predict if this is either the target of realization, the target category of interest, or if it is the remaining category. Okay, so as you've seen before, for the linear regression model, it was quite intuitive to declare what is a good prediction, what is a bad prediction, because we have real valued numbers, and the aim of our model is that on average for all observations, the predictions should be as close as it is possible to the actual realizations. So we used the squared deviation between the prediction for the target variable and the actual observation. When it comes to the logistic regression model, or this is when it comes to classification problems in general, what we want our model is that it makes a high probability prediction for the category that is actually observed. So for instance, in our data set, if, for the first observation, given some feature variables, the consumer bought something, so the realization of the target variable is equal to 1, then for this observation, we want our model to generate a probability prediction which is also close to 1. If, for instance, for the second observation, we have an example where the consumer did not buy anything, so the target category or the realization of the target variable is 0, then also for this model, we want a good probability estimation, and in this case it would mean, because the consumer didn't buy anything, that the probability for buying something should be very low for this observation. Okay, so, and this is what we need to counterbalance over all observations. We need to set the parameter estimates such that it generates high probability predictions for being equal to category 1 if we really observed category 1, and at the same time this probability prediction should be low if we observed the other category. Okay, I think and I hope this makes sense to you. Okay, so we want to actually try to say it more easily. we want to make the predictions that they really are corresponding to what we are observing. Okay, so the probabilities should be high for the actual category that we see for this observation, and this again is supposed to work for the majority of observations. So we always use like the average of all observations. How can we succeed here? We now use a loss function that is obviously different to the one from the linear regression model. We will use what is called cross entropy, or some people call it binary cross entropy. Note that this is not the single possible loss function that can be used. Also with other loss functions, but I think this is the most popular choice here. And now to better understand what happens here. So this is like for a single observation I, and assume that this variable is either 1 or it is 0. So in the first step, for a concrete observation, assume it is 1. Then we have 1 times the log of the probability prediction that it is 1. Okay, so with a minus here before. And if it is 1, then we have 1 minus 1. So the second expression here just is equal to 0 overall. If we in reality observe or have a realization which is 0, then the first expression here is equal to 0, and the second one is log of minus 1 minus the probability. So overall we have two cases, and for each case we get minus log of the probability prediction for the corresponding category. Okay, so here the category is 1. And if we have an observation which is actually category 1, then this overall expression is reduced to minus log of the probability prediction for being category 1. If we have category 0, then this overall expression is reduced to minus log of 1 minus p. So it's minus log of the probability for being category 0. Okay, and in both cases, we can take a look at the log of the probability prediction, and if it is 1, then we get low values of this expression if it really has a probability which is close to 1. And if it's category 0, then we can see that the expression which is enters the loss function is only low if we really have a probability prediction for being 0 that is quite high. So that means the probability prediction for being 1 is quite low. And this is like the aim of our model, and this is also the way that we calibrate our model. So we and as we want to do this in January for the overall for the data set, at least for all observations, we determine this expression for each observation and then use the average value here. So on average, if on average we want high probability predictions for the categories that we're actually observing. This is how this loss function works. So, and these are the only two things that are different in comparison to the linear regression model. For the linear regression model, we had a function which generates predictions, and the predictions are mapped to real valued numbers. So the prediction can be any real valued number. In comparison, for the logistic regression model, the function generates predictions with numbers between 0 and 1 that are interpreted as the probability estimate for being category 1. And then for the linear regression model, to calibrate the parameters, we minimized the average sum of, or like we add the average square deviations of predictions and actual realizations. And for the logistic regression model, we minimize the average of probability estimates from our model for the categories that we actually observe in. Okay, so this is like the two differences here. And now for the logistic model, with this loss function, we are already in a model. We already have a model where we do not have any analytical closed form solution to minimize this here. So already here we need some sort of numerical optimization techniques. And one that we already discussed about is the gradient descent method. there are also other methods available for the logistic regression model, and if you use the sklearn package, for instance, then it uses another method. But still, even at this stage and with a quite comparatively easy model, I would say, we also already need some numerical optimization technique in order to calibrate the parameters of the model. Okay, and now once the parameters are estimated, then the feature variables, if they are on the same scale, we can compare these estimates. The interpretation is not as straightforward, so it cannot directly be interpreted in terms of effect sizes. But like if the feature variables are on the same scale, what you can do is like a higher, for instance, positive value of the parameter estimate also indicates that there is a higher impact or sensitivity for the feature variable with respect to the probability prediction. Okay. Yeah, and yeah, I mean, this is maybe a little over the edge, but just to tell you, to show you the idea of feature importance as we already discussed it for the linear regression model is still here is the same. So what you basically always can ask or do is how sensitive is our model prediction with respect to a marginal change of a specific feature variable. So if on average we have experienced high sensitivities over all observations, this means we consider this to be an important variable because even a small change in this feature variable can have a drastic impact on our predictions. And yeah, just here, this is like the math given here just for completeness. But the basic idea is, again, to determine the sensitivity of predictions with respect to changes in the feature variables. Okay, so this is quite fast, but it subsumes the idea of the logistic regression model. And yeah, I think it's not as complex as it might sound if you hear it for the first time. Basically, if you understand the idea of linear regression, logistic regression just does the same, but makes sure that the predictions or the value of the predictions made are really matching the task that should be fulfilled here. And also in this way, the loss function is altered to achieve this goal. But you know, the basic idea is quite similar. So we use a kind of linear prediction function first to generate some numbers, and for the logistic regression model, these numbers have to be further processed to match the task. Anyway, if you have any questions, do not hesitate to answer me, and otherwise we will continue to extend the logistic regression model to what we will call a softmax regression, so which can be applied if we have more than 2 categories, but still will work in a very, very similar way. The only thing actually that we need to do is again to once more change the function that is used to generate the predictions. The loss function here can be kept the same. Yeah, but see for yourself in the next video. Thank you for your attention and see you soon. Bye bye.